Hi everyone, this is going to be a short video about the introduction to the definitions of limits. Textbook usually use something called epsilon delta method to introduce the definition of a limit mathematically correctly. It's here I'm approaching a slightly different way, which is still mathematically correct, absolutely correct, but it's easier to understand and gives a correct foundation, so I approach it in this way. So let me first talk about the motivation of the considering the limits. This whole calculus is started by a physicist, so it was about started from the attempting to describe the instantaneous velocity from average velocity. So average velocity is easy to understand. This is the amount of displacement over a certain period of time. So it gives you a certain idea about how fast it was moving and from one time period to another time period. And if you want more specific information, we move on to the instantaneous velocity. So this whole section's about this understanding this one, but in it naturally rises something called the concept of the limits of a function. When you do some the physics or other application, sometimes certain intuitive part is accepted, but when you do the mathematics, that part has to be rigorously founded. So we have to go to give a rigorous foundation of all the notions that is involved, and that's the difference between mathematics and physics. So if you want to understand the mathematical approach or whatever they do and mathematicians do, and you have to understand that part of the foundation. So in this whole idea of considering instantaneous velocity, the continuity was used, and mathematicians wanted to define this very continuity, and they realized it is very tricky. And then the funny thing that happened is they had to use this idea of the limits, use the continuity to define the continuity. But their intuitive notion of the concept of limits uses continuity itself, so it is kind of circling argument or a reasoning situation that is not good in mathematics. You have to be able to define either of this one independently from the other notions. So they decided to go out and define the limits without using the notion of continuity first, then define continuity using this notion of limits. So the whole deal about this definition of limits getting more difficult from than our intuitive notion is because of these two things are kind of mingled together, and mathematicians wanted to separate these two things. So that's why the definition of limit gets a little bit strange. So goal of this video, or goal of this part of the lecture, is separating these two concepts apart, limits and a continuity. So whenever it's intuitively easy to describe, and I will be sloppy and just use intuition, as long as it's clear that we're not using the continuity or we separated these two things. But there's this longer video, an hour-long video about an absolute correct approach of this limits. But next example you're going to see is the limit of a sequence, and for which I don't introduce any formal definition. It's something intuitively easy to understand, so I'll just use intuitive approach and then just point out that in it does not use continuity. So here I'm considering a sequence. So sequence is a list of numbers. So first term is 1, and that first term is denoted like this, x subscript 1. The second term of the sequence, second number, is this 1/2, and it is denoted by this x subscript 2, and third number is 1/3, and there's ... because I think you understand the pattern of this number. So fifth number will be 1/5, and so on. So if you write down the numbers like this, we consider the limit of a sequence. If I keep writing like this, and where is this position eventually going to end up at, which is often denoted like this. These numbers x1 and x2 and x3 is a third number and a fourth number. This xn will be nth number of chords. But if you keep increasing these index of this number, and then what kind of number I get if is x subscript of 1000, and of course the number is 1000th. So I think this behavior makes sense. This xn, x subscript n, this number, the nth number is becoming and more and arbitrarily close to this number 0 as we increase the index and again more and more. So that behavior is denoted like this. If we look at more and more terms is almost 0. And that is a standard notation, and this is another standard notation that as we increase this n, this sequences approaches 0, but that approaching behavior is just denoted with this equal symbol. So this is called the definition of the limit of a sequence. And again, this is very sloppy way of not so rigorous way of defining this certain thing. There's lots of questions arises, but what you have to focus on is that have we kind of used anywhere continuity of something, and I don't think there's anywhere used the continuity. And if you look at the little bit more formal definition in the longer video, and it clearly defines what we mean by something is approaching 0. The sequence is approaching 0, not using the continuity. So what I just defined over there is a limit of a sequence. And so our goal, I mentioned it earlier, our goal is defining a limit of a function. Namely, what happens to the behavior of the value of a function, not in the sequence, when we use this sequence to define that. So the goal is to define the limit of a function, and this is the beginning of the definition. So I want you to take this as the formal definition for this course, and that's how we can understand that limit of a function mathematically. First, f is a function, and we're not going to look at the entirety of the function, but just a little bit of a function. So that's just open interval a comma b, and c is a some number in it, and then we're going to define the meaning of the limit of this function at that value c. The intuitive idea of the limit is that x is approaching c, so that approaching part was the problem that used the continuity, so that's why we're doing it this way. But intuitively, as x approaches c, and what is happening to the function value f of x, and if that approaches L, and we say as x approaches c, f of x, the function value, approaches L. And here's how you get to clarify the meaning of approach not using the continuity. So here's how they did it. As x approaches c, that's the continuity part. So they wanted to get rid of that part. So what they considered is instead of the vague x value approaching c, we replace this x with an arbitrary sequence. So I forgot this part in the lecture, so I put it in there. There is a fixed value of L, the fixed as opposed to all the consideration of this sequence is L. So there is a fixed value of L as a number, and this f of x n, which is a sequence, these are the terms of the sequence. If you plug it into the function, we have all sorts of different values. If they're all approaching this fixed value, no matter what sequence you choose, as long as that sequence approaches our base value c, if you can establish that kind of fact, then we say this f of x approaches L. So here what you're supposed to observe here, and how they got rid of the notion of a continuity in this definition. Another thing that you have to notice here as an important part is this any sequence. We're not considering just one sequence or two sequence or three sequence. These possibility of a sequences that approaches C, then there are infinitely many sequences. So I'm going to use this extra space to explain this any sequences that approaches the C here. For example, I want you to look at this sequence. It's supposed to be -1, sorry about that, -1 and -1/2 and -1/3. We kind of considered this kind of equation earlier, but the difference is that it has negative symbols in it. But if you look at the absolute value, the magnitude of this number, it still goes to 0. So you can say this different sequence, the different from the earlier sequence, also approaches 0. So here's another one I came up with, a sequence that approaches 0. So I wrote it up here. What we're considering here is a sequence is approaching 0. So let me here introduce a slightly different sequence. So the first one is a 1, and the second one is 1/2, and the third one is -1/3. Fourth one is -1/4, and fifth one switches to +1/5. And Suppose I have very, very irregular patterns of this negative one and no one figured it out, but it's very, very irregular pattern. But it has all the same number, the reciprocals of these whole numbers, but the behavior of the negative is completely chaotic. Suppose we have that kind of sequence. Because of this magnitude is still going to 0, you can see that what happened to this number is this number is still very, very, very small and becomes eventually 0. So for that one, we have a third one here that approaching the 0. So we have so far three sequences, but I think it clearly suggests that there's actually infinitely many different sequences that approach 0. Not only using this magnitude, you can change this magnitude and skipping some of them, and you can easily see that there are infinitely many different ways of think about all the sequences that are approaching 0. So here's a statement, there are infinitely many such sequences. So let me go back to the statement of the definition. So here's a definition. In part it says you consider any sort of sequence that approaches C, for example, 0. And how many sequences are there? There are infinitely many possibilities. And for all those possibilities, all the sequences, if you plug in all this x value, we have a new sequence, the values of the function value sequence, and they must approach, as long as they approach 0, they all must approach as a sequence the same number. So when we establish such a fact, we cannot test this infinitely many sequences. Therefore, we have to mathematically argue, and just having this property that this one approaches C, and you have to mathematically argue that all these corresponding sequences also approach this fixed value. So that's why it's difficult to establish. And the definition itself is tricky, and establishing such a fact, it requires a lot of abstract mathematics. Okay, so most of the time we're going to be using the formulas and then theorems to deal with the problems that it's about computing the limits, and you're not going to use any of these things we talked about it here. But if you think about some foundation, the very beginning part, the proof of the very theorems that we're going to look at, some of them, and if you want to understand, okay, this is intuitively obvious and it's easy, and what you have to look at those theorems, and the reason they make a big deal out of that part, the theorem, the reason they call it a theorem is that we wanted to establish all those things without using the property of the continuity. So if you're asked to establish the continuity, and then if you're using the continuity and you're doing something wrong. So we can look at some of the theorems, and proof of which does not use continuity. But once we accept that kind of result, then you can use it to prove another result. So behind all that, the important foundation is the idea, is this definition of a limit, where we kind of substituted the continuity notion with the limit of a sequence in here. So when we say x equals c approaching, x is approaching c, what we really mean is that x is approaching c along some sequence, and we consider all possible sequences